Okay, this is continuing with section 7.2, the cross-section section, and we're going to finish with the two examples on the back side of your notes. What I've already done is I have positioned this function. So here, here is y equals 2 minus 2x, and then here's the quadratic x squared minus 1. Hit pause and go ahead and get yourself caught up. I've also found my intersection points by setting the functions equal, of course, and getting those. We're going to fill this volume, this base, with a volume that contains cross-sectional pieces that are isosceles right triangles. So I've got two legs the same here with a 90-degree angle between them. These would be 45s. And I'm going to situate that across perpendicular to my x-axis, and I'll have that isosceles right triangle sitting perpendicular to the x-axis and sitting upright then on that base. And then it will fill that space. So what I need to do is go to that volume formula where I integrate from A to B of the area of my cross-sectional piece with respect to x, because I'm perpendicular to the x-axis. Now, the biggest part, as we know, is trying to come up with what is the area of this triangle. So I think first what I'm going to do is capture what is the distance across this base. So I want the base length from the top curve down to this bottom curve, right? And I can do that by going top minus bottom. So the distance across here, top curve is 2 minus 2x minus the bottom curve, which is our quadratic, x squared minus 1. If we simplify this, we'd have negative x squared minus makes positive 1 plus the 2, so we get a plus 3, and then minus the 2x. So I've got the base length identified on this. Now, I know area of a triangle is 1/2 base times height. So I've got the base. The next step I should look for is how to get this height. And that height can come from the fact that we are in 45 once again, because this length and this length will end up being congruent as well. So what I need to do is have this. So I'm going to take 1/2 of this base length, and that would turn out then also to be my height, 1/2 negative x squared minus 2x plus 3. And then I can go into my area formula. Area equals 1/2 times the base. Remember that this full length represents the base. So I'm going to have negative x squared minus 2x plus 3 multiplied by the height, which is 1/2 of negative x squared minus 2x plus 3. Simplifying this, I would get 1/4 of the base squared. And that represents the cross-sectional area, so A of x. Now, to throw it together, the volume is representative. Now I just have to integrate from my little a being 3 and my b being 1, so I'll go from negative 3 across to 1 as I integrate those x values of 1/4 negative x squared minus 2x plus 3 quantity squared dx. Okay, so if you want to, you can put that in the calculator, and I think you will find the answer to be 8.533, and of course it would be units cubed since it's volume. Okay, last one, let's attack this one here. Find the volume of a solid formed by taking cross sections perpendicular to the x-axis that are semicircles whose diameter is the distance between these curves. F of x equals x squared, g of x equals 10 minus x squared. So I'm going to just pause and get the figure on here. Okay, so I got my pictures drawn, and maybe you want to update with me, but we've got the y equals x squared function passing through 0 down there, the 10 minus x squared, so topping out up here at 10 and opening downwards. I calculated my intersection points by setting the two functions equal, and I came up with the fact that they intersect when x is plus and minus square root 5. Now what we're going to do is we're going to use semicircles. So we're going to lay semicircles across this base so that they're perpendicular. They'll run perpendicular with this x-axis as shown here. And I'll fill in many pieces along here, all perpendicular to the x-axis, all being semicircles. Well, as I do that, as the distance across the base changes, so does the radius of our circle. So the semicircles will be smaller when they're down in this small region, or distance across the base, and then they get larger. They'll be the largest, it looks like, right on the y-axis, where we have the greatest distance from one side to the other. So, circular region, but we're only going to use half of that. So if I split this in half, I'm going to be interested in just one side of this, right? So what I need to figure out is what is the area of a semicircle. This will be the base length, or the length across the base. And that's going to come from doing the top curve minus the bottom curve. There's a pattern to this, isn't there? So my top curve is the green function, 10 minus x squared, minus the bottom function, which is x squared. So my distance across the base is 10 minus 2x squared. And that's the length across the base, which, to our semicircle, is the diameter, really, of the semicircle. And I'm interested in only half that amount, so I'm going to have to chop that down and come up with the radius being 1/2 of 10 minus 2x squared, which we could simplify to 5 minus x squared. So what I have found then is that the distance across here can be expressed as 5 minus x squared, which really amounts to the radius of each individual semicircle as it gets placed across the base. Now, how do I get area of a circle? Well, actually, area of a semicircle. Well, that's going to involve a half as well, isn't it? So I'm going to have 1/2 of pi r squared. So the 1/2, oh, and then I almost forgot my extra half. That's a circle. So now, no, I'm sorry, I'm okay. Oh, whoa. So we're 1/2 pi r squared. And now I'm going to fill in what I know. 1/2 pi is fine. My radius is coming from up here, where we calculated out half the distance across the base, 5 minus x squared. And radius gets squared, so that'll be all squared. And that will represent a of x. We are ready to do the integral part of this. Let's go find the volume. The volume of this figure, filled by cross-sectional pieces that are semicircles, will be the integral from a to b of a of x dx. And for us, we're going from negative square root 5 to positive square root 5. The area of our base, 1/2, I guess throw the pi out front too, of 5 minus x squared squared dx. And you could integrate that by hand if you want. but I put it in the calculator and I got 93.664. Very good. For homework, I would like you to attempt, let's just try to get 2 of these done and then we'll work some more on them in class. So if you could do 61A and B, give yourself a try at those. You definitely are capable of doing more because of the notes, but those will be a good starting point. And then I'll see everybody on Monday.